Use integration to determine the moment of inertia of the triangle about the big x-axis. So I have the little x-axis, which goes through the centroid of that triangle. And then I have the big x-axis, which is the base of that triangle. So I'm going to use integration to calculate the location of that centroid. Not location of centroid. I'm going to calculate the moment of inertia about the base of that triangle. All right, let's go to the next page. I have some grid paper set up here. So I'm going to start off with the same equation. We'll use black ink. I'm going to start off with I sub x, I sub big X is equal to the integral over the area of y squared times dA. So I need a differential block. If I'm looking at moment of inertia about the x-axis, I need a differential block that goes parallel to that. So this is the differential area dA. And let's see, what I need to do is figure out what that is. So this distance here is going to be dy, but then I need this horizontal distance here, and that's going to be equal to the dimension b minus x. So that's b minus x. So I'll go up here, I can say that dA is equal to quantity b minus x times dy. But the problem is that I'm going to be integrating with respect to y, not x. So having this value of x in that equation is problematic. Let's see, if I go through with that value of x in there, then the math doesn't work out. So I'm going to try and write that in terms of y. So I have an equation of a line here. I could say that y is equal to m times x plus b, the y-intercept. This is bad b. Let's make it a capital B. So it goes through the origin, so I could say b is equal to 0, and I could say that the slope of the line m is equal to the rise over the run. So I'm going to have a rise of h and a run of b, so that's x. So from that, I can solve for x, and I could say that x is equal to b times y divided by h. And so then I can bring down this differential area dA, and I can say that that's equal to quantity b minus b times y over h times dy. Okay, so now that I have that, I can go back up here. I can substitute again. Darn it. So that's equal to the integral of y squared times dA, and dA is now b minus b times y over h, quantity closed, times dy. And if I'm integrating over the area, then that means that I want to integrate from the bottom to the top. So the bottom is y equals 0, and the top is y equals h. Okay, why is this 0 down here at the bottom now instead of being minus h over 3 or whatever? It's because the axis is at a different location. So instead of integrating about this axis, the little x-axis, I'm integrating about the big x-axis instead. So that's why I'm integrating from 0 to h instead of integrating from minus h over 3 to a positive h, 2h over 3. So go back in here. So I'm integrating from 0 to h on my bounds. All right. So let's see if I can do this correctly. I can bring b out front. And then I have the integral of y squared, which is going to be y cubed divided by 3. And then here I have the integral of y cubed, which is going to be y fourth divided by 4. But then I don't want to forget about the h. And that's evaluated from 0 to h like that. So if I go in and run that evaluation, then I get b times quantity h cubed over 3 minus h fourth divided by 4h, like that. Okay, so I end up with I sub big X equal to b h cubed, and it should work out to be divided by 12. So the moment of inertia of a triangle about its base is equal to the base times the height cubed divided by 12.